The topic is similarity and dilation definitions and examples. The essential question is, what makes two figures similar? What's a dilation? And what's a scale factor? So the word similar can be described as two figures are considered similar if they are the same shape, have the same angle measures, and have proportional sides. Okay, so if you see two figures or two images, they're the same shape, their angle measures have the same degrees, and their sides are proportional, they would be considered similar. So I created a little example over here to the left to show you an example of similarity. You'll see right here I have triangle A, and right there is triangle B. Triangle B is larger than triangle A, and I want you to determine if those two triangles are similar. And to determine if they're similar, you just have to see if it fits this criteria. So are they the same shape? Yes, they are both right triangles. Do they have the same angle measures? Yes, they do. You have a 90-degree angle, 30-degree angle, 60-degree angle, and the same in triangle B. And just for the record, I didn't use a protractor when I measured those, so the degrees are not drawn to scale. And the third criteria for two figures to be similar is that they have to have proportional sides. When I'm looking at the sides of triangle A, I see that one of the legs is 2 units. That corresponding leg in the triangle B is 4 units. So right there, those seem like they're proportional, but to confirm that, we need to look at the other legs right there. In triangle A, 1.5 units, and in triangle B, you have 3 units. So the given measurements of those legs in the triangles show me that this is a proportional relationship, because all I had to do was double the side lengths in triangle A to get to the side lengths of triangle B. So what you would do if you see two figures that are similar, you can write them out like this if they're triangles. That right there means triangle. Triangle A is similar to triangle B. Go ahead and write that down, okay? So you have a nice little example to go with that definition. A dilation is a transformation in which a figure increases or decreases in size. A scale factor indicates how much to multiply the original figure by to resize it. You can think of it also as the unit rate. They're the same thing, but typically in geometry, instead of saying unit rate, they're going to say scale factor. So going back up to here to this example, since we've already determined them as similar shapes, we can determine the scale factor. What do we multiply? Let's say this one's A is the original. What do we multiply the original side lengths in triangle A to get to the side lengths in triangle B? Well, when I'm looking at this, it looks like we went 2 times 2 to get to 4, 1.5 times 2 to get to 3. Therefore, our scale factor for this particular example is 2. All right, if the scale factor is greater than 1, then your figure will become, well, let's see. See how our scale factor is larger than 1? What happened? It started out small, then it got big. So if your scale factor is bigger than 1, your figure, your new figure, will become larger. If the scale factor is smaller than 1, then your new figure will become smaller. So for example, if my scale factor right here was 1/2 or another number smaller than 1, you would multiply those side lengths by that scale factor and you would see that the new image would become smaller than the original because the scale factor is smaller than 1. So what do you think would happen if the scale factor is 1? Then your figure will remain the same. Okay? All right, for your summary, I want you to go ahead and write this down and answer it. If your scale factor was 5, what would happen to your new figure/image? If your scale factor was 1/2, what would happen to your new figure/image? Here's our first example. So you'll see we've got a segment right here. We've got segment PQ right there. And then it looks like the segment extended, and we got PQ prime. That's not q to the first power, that's called q prime. Because when you're dealing with geometry, when you see a tiny, tiny 1 like that, you would say prime, okay? Now let's go ahead and just read some information right here. If segment PQ, so from here to here, is dilated by a scale factor of 2, what's the length of segment PQ prime? So let's label this. It says PQ is 6 centimeters. So from right here to right here, that's 6 centimeters in length. Okay? And it's dilated by a scale factor of 2. And if you're curious what dilated means, we just wrote down the definition a couple of moments ago. Dilated is a transformation in which a figure increases or decreases in size. So they're saying that this right here, according to the picture, it got bigger, okay? It increased in size, and that's what dilation is, or it could have shrunk in size. But in this particular example, it increased in size. And the scale factor is 2. So scale factor indicates how much to multiply the original figure by to resize it. So here was the original figure. It was 6 centimeters, and it's dilated by a scale factor of 2. So all that we would have to do is we would take that segment of PQ, that value was 6 centimeters, and since the scale factor is 2, and we're supposed to multiply by scale factor, you would literally multiply that 6 centimeters by 2 in order to get your new length, your segment PQ prime. So 6 multiplied by 2 is 12. So therefore, segment PQ prime is equal to 12 centimeters in length. So I'm going to go ahead and label that. Okay. Don't forget your prime sign, because if you just wrote PQ is 12 centimeters in length, that would be incorrect. Okay, because it's PQ prime. Let's go on to the next example. Okay, looks like we've got another segment going on right here, and we're going to go ahead and label it like we did the previous example. And it says if segment RW is dilated by a scale factor of 1/2, what's the length of segment RW prime? So I'm going to go ahead and label what I have right here. R to W is 9 centimeters, so R to W. So this length right there is 9 centimeters. Okay. And we've got a scale factor. It's dilated by a scale factor of 1/2. So we're going to take that 9 centimeters, our original. That right there is segment RW. And you always are going to multiply by the scale factor. And our scale factor is 1/2. So we're going to multiply by the scale factor to get our new length of the segment RW prime. Okay? So 9 multiplied by 1/2 will give you 4 1/2. Okay? So the length from here to here is 4 1/2 centimeters. Okay, so just to kind of give you a little refresher of what just happened, notice how we multiplied by the scale factor right there. You multiply the original by the scale factor to get your new length. Okay, and again down here, you multiply your original, oops, I don't know why I wrote down there, times your scale factor to get your new length. So go ahead and fill in this blank. You have to blank by the scale factor to get the measurements of the new segment or segments. Right now we're going to practice dilating on a coordinate grid. So right here you'll see a coordinate grid. Another way to say coordinate grid is you might hear the word Cartesian grid. You could hear Cartesian plane, coordinate plane, or just grid. But anyway, when you hear those words, they're just referring to a 4-quadrant grid like this. You have quadrant 1, 2, 3, 4. It starts right here and it goes counterclockwise, okay? So anyway, here is what we're supposed to be doing. We have to dilate the figure by a scale factor of 2 with the origin as the center of dilation. So I see the points right here, 1, 4 is G, so I don't see it plotted yet, so we're going to have to do that. So X first, 1, and then 4. That right there is G. And then we have 3 for H. So 3, 3. That's H. And then for I, we have the point 1, 2. 1, 2, right there, okay? And that looks like it's going to be a triangle. Now we're supposed to do something. We're supposed to dilate the figure by a scale factor of 2. So if you recall from the previous notes, you are always going to be multiplying by the scale factor. So in this case, we have a scale factor of 2. So we're going to multiply all these points right here by 2. Okay? So we're going to multiply G's points by 2, H's points by 2, and I's points by 2. Okay? To get to the next, to get to the dilated image of this first triangle. So all you do is you look at the points, and 1 times 2 is 2. 4 times 2 is 8. So G prime, that's the new figure, is going to be at point 2, 8. 2, 8, and that right there was G prime. And then for H prime, whoop, I can't trace very well, I have to multiply its original points by 2, so 3 times 2 is 6. 3 times 2 is 6. So H prime is going to be at 6, 6. So 6, 6 right here. You're going to label H prime. The prime right there indicates, hey, that's the dilated image of the original. It's the new one, okay? And that last point of I prime, we again have to multiply its points by 2. So 1 times 2 is 2. And 2 times 2 is 4. Okay? So 2, 4. 2 and 4 is going to be I prime. Let's go ahead and connect those dots. And it'd be much better if I had a ruler to connect these dots, but I don't right now. Okay, so you see how these right here, you have a triangle, the original one and then the new one. I know this one's the new one because of the primes. These figures are considered similar. And the reason they're similar is because they're the same shape. They'll have the same exact angle measures. So if I did use a ruler and I used a protractor to measure the corresponding angle measures, they would completely match. So these angle measures would match, these would match, and these would match, okay? And then the third criteria is they would have to have proportional sides. So if you literally took a ruler and you measured the side lengths, you would see that these side lengths right here that correspond are going to be proportional. This side length and this side length that correspond will be proportional, and this one, those would be proportional, okay? All right, let's continue with the directions right here. So now it says dilate the original figure by a scale factor of 4 with the origin as the center of dilation. So we're going back to this original figure right here. And you'll see how it's labeled, it matches that. So I'm going to go ahead and I'm going to fill in that those original points. And the way I got those, if you're curious, I just copied them, okay? But now we have 4 is the scale factor. And as you remember, you always multiply by the scale factor. So we're going to multiply those points now by 4, okay? So why don't you go ahead and try that. See what you get. Pause the video, try it on your own. And right now I'm going to show you what to do. Okay, so 1 times 4 is 4. 4 times 4 is 16. So G double prime is going to be at 416. H double prime is going to be at 1212. I double prime is going to be at 48. Okay? So you'll notice that this new image right here, the double primed image, is going to be 4 times the size of that original image right there. Okay? So let's go ahead and plot those ordered pairs. 416. 416 is the point for G prime, or sorry, G double prime. Then we have 12, 12 for H double prime. Oops, sorry, I can't find the number. And for I double prime, it's 4, 8. Oops, did I have that 4? Okay. Okay, I'm going to go ahead and connect the points. And if you do have a straight edge around you and you're not holding a video camera, you should go ahead and use it to connect your points. Okay, so you'll see how these 3 figures are all similar to each other. They will have the exact same angle measures, it's the same shape, and they'll have proportional sides. Okay? And there's one more part I do want to show you. And it is this part where it says, the origin as the center of dilation. And what that means is, if I took, the origin is at 0, 0. If I took, let me find something to take here. Here's some paper. If I went and had a straight edge from point 0, 0, and I lined up the the H's. So, let's see, where's the H's? That's an H, right? Okay, the point's H, 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 H. See how it goes through the origin and it hits the points. And the center of dilation is at 0, 0. And same with the points, the I points. So here's I prime, I double prime. Through the origin, if I connected those dots, oops, keep moving it, sorry. Go straight through. And for the G prime and G double prime, through the origin. Ta-da! Okay, so that's what it means by the origin as the center of dilation. Like they all kind of go back to it, okay? All right, turn the page, please. So in the previous example, we talked about the origin being the center of dilation. So, you know, the point 0, 0 was the center of dilation. I'm going to show you how to dilate an image when the origin is not the center of dilation, okay? So right here is the directions. We have a trapezoid right there, which is also a quadrilateral because there's 4 sides to it. But it says dilate the figure by a scale factor of 1/2. So you know we're going to have to multiply all those original points by 1/2 because you always multiply by the scale factor. And something that you should remember, since the scale factor is less than 1, what's going to happen to the shape? It's going to get smaller because whenever the scale factor is less than 1, your shape will get smaller. If the scale factor is bigger than 1, it would get larger. But anyway, they want point W as the center of dilation. So I am zooming out right here. You see here's point W. What I want you to do with a marker or something that you can see with, I want you to make point W the center of dilation. So what that means is make that 0, 0 basically, okay? And this is kind of challenging for some people because you do have to ignore the original X and Y axis, okay? It takes it a little, it extends what we've been doing a little bit farther for those of you that need the challenge, and I know many of you do. So right there, you made that the new 0, 0. You're going to ignore all this stuff right here. So this now is 0, 0 because point W is the center of dilation, okay, in this particular example. So now you see the shape over here, the trapezoid. We need to fill in what ordered pairs are used for point A, B, and C, okay? So here's the hard part, well, semi-hard. You have point A right here, okay? And some of you will be like, oh, it's over here, 1, 2, 3, 3, comma, 1, 2, 3, 3, negative 4. But that's not the case. You have to ignore this old original coordinate axes right here because this is your new one. So this right here is 1, 2, 3, 4, 5, 6, 7, 8. So I know right here, this point right here is 8, comma, 1, 2, 3, what's negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8. So it's 8, comma, negative 8. Okay? Remember, ignore the old one, the old X and Y axis. Okay, so now we have point B. Do the exact same procedure. This is 0, 0. So we're going to count and find what the ordered pair is that represents B, okay? Go ahead and do that right now and see what you get. And I think you would get 12, negative 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. Okay, so we got 12, negative 6 for B. And then let's go ahead and look at C. So I know it's at 8 already because it's on the exact same segment as A. And it's going to be negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, negative 9, negative 10, negative 11, negative 12, negative 13, negative 14. So 8, negative 14. I hope you're paying attention because the next example you're going to do it all by yourself, okay? Okay, this next point, so B was at 12, so this would be 12, 13, 14, 15, 16. 16. Common negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, negative 9, negative 10. Okay, so now that we got that all taken care of, I'm just going to label this. Okay, so we got that taken care of. Now it's time to do the dilation part where we multiply by the scale factor. And again, the scale factor is 1/2. So you're going to take all those points and multiply them by 1/2. Okay? So I want you to hopefully remember this. Whenever you multiply by 1/2, it's the same thing as dividing by 2. Multiplying by 1/2 is the same as dividing by 2. And that's what I like to tell myself, because sometimes I forget, or sometimes it's hard for me to multiply by a fraction. But when the numerator is 1 in a fraction, you can basically divide by the denominator. Okay? All right, here we go. So half of 8 is 4. Half of -8 is -4. Half of 12 is 6. Half of -6 is -3. Half of 8 is 4. Half of -14 is -7. 1/2 times 16 is 8. 1/2 times -10 is -5. Okay, so you're going to see that this shape is getting smaller. It's going to be half the size of the original shape, okay? And remember, you're ignoring the original x and y axis, because this right here, that's the new one. That's the center of dilation, so that's what we're all going toward. So 4, -4 from this point is going to be a prime. 1, 2, 3, 4, and then -1, -2, -3, -4. And again, that's going to be a prime. B prime is 6, -3. 1, 2, 3, 4, 5, 6. -1, -2, -3. There's B prime. C prime is at 4, -7. 1, 2, 3, 4. -1, -2, -3, -4, -5, -6, -7. That's C prime. And then D prime is at 8, -5. 1, 2, 3, 4, 5, 6, 7, 8. 1, 3, 4, 5, -5. Okay, so connect your points, please. Use a straight edge if one is available, otherwise your shape will look really distorted, maybe like mine. Okay, so that's what it looks like, and since that point W is the center of dilation, watch what happens. So I can take a straight edge, hopefully this paper's straight, and I can line it up with W, and when I can hit all through the A and A prime. Same with every point on there, because that's the center of dilation. So it all goes toward that center of dilation. So see those B prime and B, and then same with the D and D prime. Line up the points, point, 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 and the C's also. See, point, 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 all going that way, okay? All right, the next page, you're going to be doing that on your own. So use this as a reference, this example as a reference, okay? This is when you're dilating when the origin is not the center of dilation, okay? Okay, on this last page, you're going to practice to see if you understand what to do if the origin is not the center of dilation. So I'm going to just kind of walk you through this. I'm not going to show you the answer because I'm going to correct it when I see it. But it looks like we have another quadrilateral of a trapezoid right here. And you're going to dilate the figure by a scale factor of 1/2, so similar to the previous example, but this time it's going to be point R as the center of dilation. Here's point R, okay? And you'll see that you have blank ordered pairs right here that you need to figure out. So you should pause the video and try it on your own. If you're like, I don't know how to do this, please remember the previous example. The first step we did when we knew that the origin was not the center of dilation was, since it was W, you made that the new 0, 0. Okay, so that's 0, 0. You ignored the old x-axis, you ignored the old y-axis. Your first step was to find the ordered pairs of the shape, okay? So you'll find the ordered pairs of that shape, write them down, and then you're going to multiply by whatever the scale factor is. Once you get your new points, you're going to plot them. And where you're going to plot them from is from right here. Ignore the old y and the old x-axis, okay? And that's what you'll do. To check your answer, to make sure that point R is your new center of dilation, and to make sure you didn't mess up with plotting your points, remember that you can take a straight edge, just like we did previously, and from your center of dilation, it should go through your corresponding points, okay? And if for some reason I had like, if I was doing this and I was like, okay, there's the old B, and there's the center of dilation, and then you had B prime like way over here, and it wasn't even lining up, then you know you had made a mistake, okay? So So go ahead and do this. You can do it. Have a good day. Bye.